Uh, Good morning. This is good to give a talk after you have had your coffee, so it's good that Chuck changed the schedule of the talk. And then again, I saw two of my public health professors here in the audience, and I actually went to one of them and said, okay, would you mind if you step out, go just out? It's nothing new for you. You were my professor just uh, till 2 years ago. So if you are not a professor of public health, that's okay. Just please be seated. But uh, very introductory stuff. It's a general overview of what we do to decide on the statistical test that we use for inference. And my purpose is to help you choose, not perform the test. So nothing hands-on here. It's just an overview of what helps me decide a t-test or ANOVA or ANCOVA. The steps that I take to decide on the statistical tests, it starts with the conceptual model, or in this field, people call it also biological question. What is the biological question that you are working on? Do you have any, or it's just an exploratory approach to some data? And to know the conceptual model, a very important step of part of it is your study design. And you to run some hypothesis or test some hypotheses, you should know all about your variables, including the role of each variable in your study and its type or level of measurement and its distribution. So I start with the approach. Again, if you have a hypothesis, your hypothesis might be an association, which is very different from prediction. Or you may have difference to test the difference or a change over time. And design questions, some important design questions that we may be looking for before making the decision for our test is, do you have one group, two groups, or multiple groups? And do you have paired samples or independent samples? Another question is, do you have any covariate in your study that you want to get rid of their effects? And do you have time in your study design or not? And as I said, is the data or are data nested and clustered or independent? So these are the questions that we ask before deciding related to the design and conceptual model. And then related to variables, some of the important questions are, what is our independent variable, what is our dependent variable, and what is the covariate? So defining the role of each variable is very important to begin with. And then I usually see my variables as either primary variables that I am interested in, even if they are moderators, or those variables that I'm not interested in, like covariates. And that determines how you structure your data. Do you put data as long or wide? So if you have paired individuals or paired observations, you use another structure of data for just collecting your or entering your data to the data set. And over my talk, I give you some examples of t-test or correlations, and I'm using this data set that we published with Dr. Evans as principal investigator of the study and also Chuck on the study, that this is the hypothesis that Dr. Evans is working on is lipid profile contributes to mental health, particularly for patients with a psychiatric disorder like bipolar disorder. So just to give a sense of the data set, we collected data on almost 100, depending on the research questions. For some research questions, we have higher sample size. So something around 100 individuals, some of almost half of them bipolar disorder and some of them controls. And we drew fasted blood, and then we measured some mental health questionnaires like depressive symptoms, life functioning, quality of life type of thing. Here in my model that I'm reporting, when I'm giving an example, I am looking at one of the mental health or health outcomes, which is life function questionnaire. And that in that measure, it simply measures quality of life. Higher score is a bad thing. So higher score, worse outcome. And when I say the first step is to decide on the conceptual model, in my example, am I asking, for example, linoleic acid contributes to function, or am I asking bipolar disorder changes how linoleic acid contributes to your function or mental health, or I'm asking the way bipolar disorder influences your function, at least in part, is due to linoleic acid. So with this type of same variables, I'm proposing three different biology questions or conceptual models. The first one is just the main effect. The second one is a moderation. So the moderator is very of interest. And the third one is a mediation. And in all these, we are using age, body mass index, and sex as confounders. Of course, some of our patients with bipolar disorder are using medications, but just for simplicity here in our real work, we also control for medications for some of these. For example, it's difficult to control for medications in this conceptual model too, because not everyone is using a bipolar medication. So the conceptual model dictates the covariates that you can use, but what we are proposing here is just age, BMI, and sex as covariates. So variable role, as you know, maybe better than me, we use some interchangeable terms for these, like we call independent variable or predictor, and we mean the same thing, or dependent variable and outcome with, again, some type of the same idea. And then in epidemiology, we call moderator and effect modifier. So if you are interested in the role of your third variable as a moderator, you may call it effect modifier, or suppressor, which is a variable that when you add it into your model, an association which is missing shows up. So suppressor is some type of reverse to mediator, that in mediator, when you add that variable to your model, the association weakens, but suppressor, when you add that variable, the association becomes stronger. Or different names for third variable as confounder, control, and covariates, almost the same thing. Here I am giving you 4 examples for hypotheses if your approach is not exploratory. The first one is 2 averaged or mean or proportions differ. So in the first one, there is no time, and there are 2 groups, and the hypothesis is difference between 2 either proportions or average. So for that one, we use 2-sided t-test or statistical test because we don't have a directional hypothesis. For the second one, we propose that average in group A is larger, not different, larger from the other one. So we have a directional hypothesis. We use 1-sided t-test or 1-sided statistical test. And then if you have one group and you are interested in the change in your outcome, either it is a proportion or average, So this is the third model you are looking at. And if you have multiple groups and there is a time variable which observations change or followed over time, it's the last one. So you see how you can depict the hypotheses using very simple graphs and then add the covariates to see which covariates you need to control. There was a lecture yesterday on design, and just this slide is a short overview of role of the variables, or just a variable view of those designs, some of the important experimental design. If the design is a pre-post, you have one group with at least 2 observations. So you see the same individual has a repeated measure just one more time. If you have an RCT, you have 2 groups at least with at least 2 observations. So there is time and there are at least 2 groups. And then if you have time series, you have at least one group with more than 2 observations. So you see how maybe you can better think about your variables and the structure of the variables in your data set. And another aspect of the variable, important aspect of the variable, is level of measurement. The variable is either numerical, if continuous, or interval. Continuous is a variable that can get any value in a range, and then interval can just get the whole numbers. And categorical, nominal, and ordinal. Nominal being classes or categories which don't have any relative or proportion to each other, and then ordinal, they have an order to them. And that determines what we report. Do we report mean and standard deviation and range, or median and interquartiles, or frequency and percentage? So one example of the variable interval, in most of our studies, we don't say someone was 20.5-year-old. So in age, in most of our studies, is an interval. And for nominal, some examples for you is, for example, an intervention, or a group or an arm, which all are the same thing, just in different disciplines, or sex and race, which some of them are covariates or genes. One important thing here is the dichotomous variable and dummy variable. When a variable is coded as 0 and 1, we usually call it dummy variable, dichotomous. And if we have and if we have a categorical variable with multiple classes and we want to use it in as series of dichotomous variables, we usually come up with n-1 dummy variables. For example, if we have 4 countries, we define 3 dummy variables and we use them in our model. So dichotomous and dummy variables are part of nominal variables, specific part of the variables. And then ordinal, some examples, BMI classes. So underweight, proper weight or normal weight, mildly overweight, severely overweight, and morbid obese. So those kinds of classes, or the dose of an intervention. If you are interested in the causal effect of one variable, dose effect, dose response association is very important for you. So you are not only interested to show that the intervention has an effect, you are also interested to show that the dose of an intervention also changes the outcome. So you may be interested to redo your hypotheses, testing in using an ordinal variable with intervention, like no intervention, low dose of the program, and high dose of program. The same for program attendance. How many sessions the individual attended your weight reduction program, none, between 0 and 10 sessions and more, for example, an ordinal. And then you can also use illness severity, like mild, moderate, severe, as an ordinal variable. So that was the introduction for what we need to know about our variables and our conceptual model or biological questions before we approach our data. But to look at the data, we usually start with descriptives. And we do some exploration. We use box plot. We may use a scatter plot or histogram to see what is the distribution. Is there any outlier or not? And then after we are done with our descriptives, we go forward and we conduct our bivariate analysis, which suggests, meaning that there are two variables without any control in our model or hypothesis. And then if there is a covariate or a number of covariates, then the next step is multivariable analysis. In many papers or many documents, I see use of term multivariate analysis for here, but the correct term is multivariable. So when you have multiple outcomes, you call the modeling multivariate, like PCA. But if you have multiple predictors as just one outcome, you call it multivariable. So by exploration of data, and we get a sense of distribution of our variable. Here is an example of a perfectly normal variable, which we never see. And you see that the proportion of the individuals or observations which are between average and one standard deviation, for example, 34% of the observations are, if the distribution is normal, is usually there. And then if you are interested in using a statistical test to see if the distribution is normal, that is the test, Kruskal-Wallis. And then what is the benefit or why we look at the distribution to see if it is normal or not, because it defines or determines should we use a parametric or non-parametric test, a statistical test. And if in some disciplines, if sample size is at least 30 in each group, then some reviewers or we are some type of allowed to use parametric tests, but it's very specific to the discipline. And then I just wanted, I know the more detailed discussion on missing replacement, imputation, data imputation, and those kinds of things would be covered by George. But I just want to refer to the point that the shape of distribution would be changing based on the way you impute your missing data. If you replace your missing data by mean, you are just adding to the peak of this shape, which would have some implication for a t-test, not necessarily for a correlation. So. And okay, if the data is not normal, we usually describe the shape of the distribution by two characteristics, skewness and kurtosis. For skewness, it describes the symmetry of the shape of the distribution, and some numbers, again, in some domains, some disciplines accepted. So if it is close to 0, it is close to normal. If it is up to 1, it is a very good distribution. And if it is up to 3, acceptable. But if maybe larger than 3, you need to do some transformation of that variable. And then that's the formula, one formula for defining skewness, that 3 multiply the distance between mean and median divided by a standard deviation. So that's how you can calculate that with hand. And here you are looking at distribution of the variable that I'm using for my experiment here, linoleic acid. And as you see, it is not normally distributed, but we don't want to do further transformation. So we are using this data, this variable. And as you see above, if the data is positively skewed, most of the data is on the left. And when the data is negatively skewed, most of the data is on right. And you see the location, relative location of mode, median, and mean when the data is skewed. So you get a sense of, for example, mean is larger than median, and median is larger for mode there in a positively skewed data. The second characteristic of the shape of the distribution is kurtosis. And it doesn't talk about symmetry, but talks about the flat or sharp peak. And if it is high or positive kurtosis, it's sharp and then declines rapidly. And if it is low or negative, it's a flat top. And you can expect that the association or a t-test would behave differently when there is a peak and a sharp decline. So you have a higher chance of getting a significant p-value when it is positive kurtosis. So the other topic that I want to just cover here is finding an outlier. You can use univariate or bivariate exploration to find an outlier. The graph on top is one example of just using a univariate exploration to find one. And the second graph is using a scatter plot to see if most of the observations cluster together, but the way x-axis or the x variable and y variable is correlating is not similar on that case. So you may want to find your outlier using a univariate or bivariate approach. And some people use a cutoff of 1.5 interquartile above the quartile range, or lower than the, so 1.5 interquartile lower than lower quartile, which is the V-square of the box. So as I said, you may need to use a box plot for your description or exploration of the data distribution, and it talks about or shows that how skewed or how spread the data is. And as you see, you can define your box plot in different ways, but this is an example that a very accepted one, Tukey box plot, and the median and the quartile range and 1.5 interquartiles above and lower those quartiles as V-scales. And if the data is positively or negatively skewed, we need to transform the data. For positively skewed data, one approach, a very common approach, is logarithmic transformation. And here you see some examples that this is the original distribution, and this is after. So you see how the shape has become more normal. Or in this case, it has become more normal after logarithmic transformation. And another transformation of the data is Z-score. So you you assign 1 to standard deviation and -1 to minus the standard deviation and 0 to the average. So the formula is your observation or your value minus average divided by standard deviation. So that gives you a z-score. One benefit of using z-score is when you want to do a prediction model. For example, you want to use a combined set of biological markers that their range and their distribution is very different. So you may not be able to add glucose to linoleic acid to predict heart disease, but you may be able to do it when you have their z-score. So if you are interested in a sum score of different biological markers for a prediction formula, a good way to do it is through standardizing these measures or bringing them all together and then using them in one regression model, for example. And before I start a very brief overview of statistical tests, here is a website that many of us use, and maybe you are also familiar with it. ATS at UCLA provides a very good explanation of the statistical tests, examples in using different software packages like SPSS, SAS, R, Stata. So that's a good resource. Again, what we do to decide on our statistical test is we define our conceptual model or causal diagram, even if the association is not causal, but we draw it as a causal diagram. And in epidemiology, there is a term or approach, DAG, Directed Acyclic Graphs, or DAG, which is a diagram of the association between the variables that helps you decide what variable to control for or what variable not to use as a strata, those kinds of things. Colliders and other roles of the variables based on that. And by that causal diagram, you already know that what is your independent variable, what is your dependent variable, and what is the third variable that you want to focus on or get rid of. Or do you want to do bivariate or multivariate? So the first statistical test that I'm reviewing here is an independent sample t-test. When the distribution is close to normal, two groups, and you want to compare average. So as you see, there is no time here. It's not comparison of lipid profile before and after intervention, because it is not independent sample, so they are related group of people. If distribution is not close to normal and you can't assume those, or you don't have those assumptions, you can use its non-parametric alternative, which is Mann-Whitney test, which doesn't compare mean but compares median. And again, the groups should be independent, so it is not appropriate for testing change over time. And in some disciplines, people agree on the sample size of 30. So if your sample size is 30 in each group, you may be able to publish a paper when you are using t-test, independent sample t-test, and when you are coming down, the reviewers get more tough using independent t-test. So that's a rule of thumb here. And then using the data set that I explained in the beginning. Here I am running 3 independent sample t-tests to see if I need to control for any covariate or anything in patients with bipolar and controls. Here you see 0 for controls and 1 for patients with bipolar. And for example, as I said, the sample size is larger here, just larger, the same data set, but higher number of individuals entered this analysis. As you see, the average age is almost the same for controls and bipolars, and as you come down, there is no significant difference. And if you look at the BMI, the average BMI is at the margin of being obese on average for patients with bipolar, but only 26, so 4-point body mass index difference. So here you see it's significantly different. And to pick the p-value for the independent sample t-test, the one you use depends on the assumption of the equivalence of the variance of the 2 subsamples. I don't want to go to the details here just because it is an overview. So, but what if the participants are twins, or it is one individual pre-post, so it is not independent sample? So if you are comparing 2 groups which are related to each other, you run pair t-test to compare average. One example is you have run your sample or you have measured something, and you believe that the next time you have you want to test if you measure it again, that would be exactly the same value of the same individual. So type of reliability. For that research question, we shouldn't do independent sample t-test because this is the same measurement of the or a measurement of the same individual. So when you are testing reliability, 2 measurements of one individual, you need to do pair t-test. But still, you have just 2 groups. If you are interested in the correlation between 2 variables or associations, so as I said, our approach is being dictated by our hypothesis. The hypothesis is not change over time, but is just correlation at each time point. We use either Pearson or Spearman correlation. And on top, you see graphs which are showing positive correlation, 0 correlation or no correlation, and negative correlation, which suggests that while X is increasing, your outcome is also increasing. An increase in your predictor or independent variable doesn't make any change to the outcome, or while X is increasing, Y is decreasing. And then here, you are looking at the actual observations to see to get some sense of a strong to moderate correlations. And this is my actual scatter plot using Simon's data to see if the correlation between linoleic acid and life function, or one measure of quality of life, or how you can function in life, depends on your bipolar status. So illness changes the relevance of linoleic acid to your function. And the dots in green are bipolar, and those in blue are controls. And as you see, the first observation is that those with blue are at lower level of LFQ. So LFQ, as I said, higher score, a bad thing. So those who have bipolar disorder have higher LFQ, which is worse outcome. And then, as you see, there is some mild negative correlation between linoleic acid in serum and life functioning or quality of life if you are bipolar, but not if you are controlled. And that was the scatter plot, and this is Pearson test based on the group membership. So here, controls, I am looking at the Pearson correlation of life function and linoleic acid in serum, and you see it's far from being significant, and the association is close to 0. And for bipolar, as you see, there is some type of good correlation, which is significant. So, but what if we have more than 2 groups? We run, again, for here, we don't have time. We don't have multiple observations over time. We have just average or a distribution which we want to compare across multiple groups. We use ANCOVA. And when ANCOVA is significant, it just tells us at least 2 of the classes are different for our observation. It doesn't say or tell us that all classes differ from each other. So if we got a significant p-value for ANCOVA, then the next question is, what is the difference at which groups are actually differ? And then we run post hocs. So post hoc is only needed when you have a significant ANCOVA to find which groups are really different. And then for if you have multiple groups and you have covariates, so if you want to, you don't have time, you have independent samples, multiple groups, and you want to compare the distribution of a numerical variable, but you have covariates, you can use ANCOVA. And chi-square. Chi-square is being used when you want to compare a nominal variable or categorical variable across at least 2 groups. It allows you to compare multiple groups. And for example, if I want to see if the 2 groups that I'm using, patients with bipolar and controls, vary based on gender, or sex, I need to control for sex, I use chi-square. One important thing, again, like ANCOVA, when the p-value is significant, it tells you at least 2 groups are different for that proportion. So you need to go forward and explore which groups differ for that proportion based on a chi-square. An example of chi-square is here. As you see, individuals, controls, and patients with bipolar, 58% of controls are female, and 75% of the patients with bipolar are female. So as you see, it's not that difference, and you see the p-value here. The caveat here is you need to have cells which their expected value is at least or is at least 5. If 20% or more than 20% of the cells have an expected value of less than 5, you cannot use chi-square, which I will explain. So if we cannot use chi-square for that reason, as I said, the alternative is Fisher exact test, which ALA has one of their application of Fisher exact in her presentations. And then one important thing here is you need to merge classes before you can use Fisher exact as an alternative to chi-square, because Fisher exact only allows you to do 2x2 comparison. So chi-square lets us do comparison of 4 groups, 5 groups, but not Fisher exact. And McNemar test is being used when the observations are not independent. So if, which is a common mistake in the literature, I have seen a lot of papers that use chi-square in an RCT or before-after study, comparing a proportion of the same group before and after an intervention. If the individuals or observations are not independent, for example, they are the same individuals, we need to use McNemar chi-square. The application of chi-square would be wrong. And the bivariate tests are ended here. I have 3-4 slides on multivariable, again, not multivariate, multivariable statistical tests. One of the common ones is different types of regression. Regression is being used when you have multiple predictors or independent variable and just single outcome or dependent variable. And the types are listed here. Some of the types are listed here. Linear regression, when your outcome is numerical or at least an ordinal variable. Different disciplines define it different way. At least 5 to 7 classes of an ordinal variable lets you use a linear regression, preferably 7 classes of or orders. Logistic regression, when your outcome is a binary variable, is coded as 0 and 1. And then Poisson, as if your outcome is count, like number of hospitalizations over an RCT or a long cohort. So as you see, the outcome is interval, not continuous, or should be just whole numbers. And Cox regression or proportionate hazard model, which let us model time to an event, like time to first heart attack over time. If a lipid profile predicts time to first heart attack, that's the model to use. And then if the outcome has multiple categories but not ordinal, we use polynomial. So for linear regression, as I said, at least 5 to 7 classes of an ordinal variable. You get usually an R square, which is the proportion of the variance being explained by the whole model. You can run it in a block manner or hierarchical manner. You can first control for your demographics, then you can add your socioeconomic factors, and then you can control for body mass index and other factors, and then you can add your predictor of interest. Or you can just run all of them at the same time. The assumptions, there are multiple assumptions for using linear regression, but 2 important ones is, first is no multicollinearity, so the variables shouldn't be correlated strongly. The second one, which is again sometimes mistakenly used, is normal distribution of residuals, not necessarily normal distribution of a predictor or the outcome. So the more important part is the model should behave similarly across levels of your predictors. So normal distribution of the residual is the most important part of the assumptions for linear regression. And then if it is longitudinal data, and for example, linoleic acid has changed after our intervention, say weight loss program, we have two ways, at least two ways to model this data. First is to consider the post-test as the outcome and control for pretest. So you are not calculating the difference score, and you are modeling the post-test and using pretest as a covariate. The second way to run the same or test the same hypotheses is a difference score, which the results mean totally different things. So in that case, you don't necessarily need to control for baseline or pretest. This is one example of the Dr. Evans' data of running simple linear regressions among controls and patients with bipolar to see if the behavior of linoleic acid or contribution of linoleic acid to life function differs for patients with bipolar and controls. As you see here, among controls, I'm jumping to the p-value here. For linoleic acid in serum, there is no association between LA serum and life function for controls, but while sex, age, and body mass index is controlled, but you see a good correlation after adjusting for body mass index, age, and female among patients with bipolar disorder. So linoleic acid contributes to mental health of patients with bipolar, but not controls. And as I said, when the outcome is a dichotomous or binary coded as 0 and 1, the way to go is logistic regression. It doesn't give you an R square, but there are ways to get pseudo R square. So there are ways to guess or show the overall function of the model in predicting your outcome. And logistic regression is being commonly used for when you have a prediction aim. So if you say, I have 5 biomarkers, 5 fatty acids or 5 lipids that would predict first time to heart disease or would predict heart attack, your outcome is a binary outcome, and you are not interested in the association of those factors with your outcome, but you are interested in using those factors to predict something with substantial or good accuracy and sensitivity and specificity. One way to do it is to use a logistic regression. Divide your sample in 2 pieces, just for now, say 2 halves, and then call one half of the sample derivation set and one part of the sample validation set, and train your model or run your model or find the best working model in your derivation set, and then bring the same model to validation set and rerun it. And that process would give you a 2-by-2 table which shows those people who had the illness or condition and the model successfully predicted them, so they are true positive, and those who are true negative that didn't really have and model predicted them as not having the condition, and the other 2 like false positive and false negative. And these are the formula that gives you first what is the rate of true positive, false negative, sensitivity, specificity, and then accuracy of your model. So if your hypothesis or aim is to find a prediction model, you use logistic regression and you divide your sample into two pieces, and then you define these statistics. And as I said, the data may not be independent. For example, observations may be nested to individuals, who those individuals may be nested to doctors over time. And we know that different doctors practice differently. Some will prescribe lipid medications more than others. So if we want to run a model in a large sample, which is nested and is not necessarily independent, then we need to run mixed effect regressions, which also similar to hierarchical regression model or HLM. As I said, one example is cohort with multiple individuals, that those individuals are living in different cities or attending different hospitals. My slides, the presentation ends here, but I have a few examples for you that I just want to overview them for you that you may use later. The first one is I have provided you a slide with some examples of level of measurement. For example, as you see, BMI can be operationalized or treated as a numerical, ordinal, or nominal variable. I also went to PubMed, Medline, and searched some papers to find lipid profile in the title to help you think the conceptual model or play with the conceptual model of these studies. For example, serum lipid levels and cognitive change in late life. In that study, without reading it, most likely serum lipid profile level is the independent variable and cognitive function is the outcome, most likely. So, and then the rest of it. Some have genes, some have groups, some have time. So it's good for practice. And then, as you know, lipid profile may be an inclusion criteria. So it is not a variable in your study. It might be an independent variable. It might be a mediator. It might be a moderator. So the lipid profile, baseline lipid profile may alter the effect of your intervention on the outcome. So in that conceptual model, lipid profile is your moderator of interest. And then some write-ups of group differences, an example with twins over time for practicing conceptual models or biological questions, and some hypotheses, and just one example of a moderation. So as you see, slope or correlation coefficient varies based on group in the graph here, but the slopes are the same here, just the baseline or intercept is different. So I think my presentation ends here. And I will take questions. I know it was very introductory and boring, so sorry. Yes, I had that. Yeah. you are interested to have an algorithm, very rapid algorithm that, for example, type of what I'm hearing, that what is the level of measurement, number of groups, and then the test. Yes, there are some algorithms that I can just add to my slides if you are interested to have them. Yeah, such an algorithm becomes extremely complicated very fast. So it is a lot of more tests. Yeah, that's the problem.